today we have a great pleasure to have Ryosuke Hirai from the RIKEN and Monash University. So Ryosuke now is a SPD at the Spatial Postdoc Research at the RIKEN, and he most of the time working in the Australia in the Monash University. He got his PhD from Waseda University in 2017. And this university is very special because he was studying from high school and to undergrad and to master to PhD, all through this Waseda University system. So, and later he got the JSPS postdoc fellow for research in the Oxford. Then he got another postdoc position at the Monash University. Now he's still working at the Monash University. And Ryosuke is an expert on this stellar evolution, especially focusing on the binary interactions. And today, Ryosuke will talk us about the supernova and the binary interactions. So let's welcome Ryosuke.
Thank you very much for the introduction. Yeah, I'm Ryosuke Hirai. You can just call me Rio. I'm a RIKEN postdoc, but mostly spend my time in Australia, so please let me know if you ever come to Melbourne or anywhere in Australia. I am going to talk about supernovae and binary interactions. But yeah, so basically I am mostly a stellar astrophysicist working on stellar evolution, and I've heard that many of you work on galaxies or other aspects, so I just wanted to start with some of the basics of stellar evolution, just to set the scene. So this is one diagram of how stars evolve. Basically what a star does is they form, they expand, and they die. And that's all they do. The way they die depends on what the stellar mass was when they were born, but my main area of interest is in this high mass regime where the initial stellar mass is above, say, like 8 solar masses or more. And in this case, after they expand, they undergo this thing called core collapse. So they create iron in their core, and then the iron core collapses due to its own gravity once they stop fusing elements, and then they cause this super energetic supernova explosion, and they leave behind compact objects like neutron stars and black holes. Now, in this massive star regime, this actually doesn't really work. And this is because most stars actually are in binary systems. So we know that roughly about half of all the stars in the universe are in these so-called binary systems where two stars orbit around each other. This is just the background picture is a famous scene from Star Wars, where this is the planet called Tatooine, where Luke Skywalker grew up. But basically, this is like half of all the stars in the universe. You know, other stars other than the sun. So the sun is a single star, but most stars, well, half of all the stars are in binaries. However, this binary fraction is known to increase with mass. So if you look at this plot where the binary fraction is plotted against the primary mass, so the mass of the primary star in the system, you can see that, well, for the sun, yeah, the binary fraction is about 50%, but at the massive star end in the B star, O star regime above 8 solar masses, you can see the binary fraction is like 90% or even reaches up to about 100%. So single stars actually are somewhat hypothetical objects in the massive star regime. And what's more, if you look at the triple and higher order multiple fraction, roughly about, say, 60 to 70% of all massive stars are in triple systems. So actually, even binaries might be a rare thing. So most stars are in triples, then there's a small amount of binaries, 0 single stars. Now the more important thing is, well, if they're in binaries, how close is their orbital separation? And from some observations and some modeling, it's known that about 70% of all these massive binaries have orbital separations close enough that the stars will inevitably interact with each other during their lifetime. So, yeah, I said single stars are kind of hypothetical, but well, about 30% of massive stars still, even though they're in binaries, they can evolve without ever experiencing the impact of being in a binary, but 70% of them will all go through some form of binary interaction, which drastically changes the course of their evolution. So what is a binary interaction? So there's many different forms of binary interactions that could happen. Here I'm just listing a few major forms of binary interactions. So one of the main ones is so-called mass transfer, or what we call Röslow overflow. So as I said, stars towards the end of their lives start to expand to become red supergiants or red giants. But once they start to expand too much, their outer envelope starts to get gravitationally bound to the companion star, so it starts to slowly transfer mass to its companion. And if this process, goes stable, we call this stable mass transfer, and then in the end you dump most of your envelope onto the companion star, so you change the mass ratio and so on. But if this mass transfer process is not stable, so the more you transfer mass, sometimes the star wants to expand even further, and the orbit shrinks rapidly due to energy and angular momentum conservation. So in some cases, the star engulfs the companion star into this so-called common envelope phase. So basically, this is stellar cannibalism. The primary star eats up the companion star, and then the binary rapidly shrinks to become a super tight binary. Now, in some cases, the orbital shrinkage releases enough energy to eject the envelope, so this leaves behind a tight binary, but sometimes you can't eject the envelope, you just don't have enough energy or angular momentum to do this. The stars will just simply merge into a single object. Now what kind of mass transfer, what kind of binary interaction the binary experiences and what the outcome is strongly depends on the initial parameters, like the masses of the two stars and the orbital separation, eccentricity, metallicity. And because there's so many parameters involved, there's a huge diversity in the way binaries can evolve. So here I'm just showing an example of, this is a diagram showing just a small fraction of how massive binaries can evolve depending on which form of binary interaction they experience, what their outcome is, and what kind of observables we can expect. So here you can see, you can have a massive binary that goes through either stable mass transfer or common envelope phase, and in some cases you can eject the envelope to stay a binary. Sometimes you become a single star, but eventually, if you have a massive star, one of the stars has to explode. So you have a supernova explosion, and that again drastically changes the evolution. Sometimes even after the supernova, the binary can stay a binary. Sometimes you disrupt it. But if you're very lucky enough, if you go through a very thin pathway, you can eventually form so-called double compact objects, which we observe as gravitational wave sources, or like gamma ray burst sources, or kilonova, and so on. So each of these different panels on this diagram actually represent individual areas of research. So many people dedicate their lives just studying like one aspect of these, the life of a massive binary. For example, many people spend their whole career studying supernova or X-ray binaries or gravitational waves. My research approach is to actually try to kind of connect the dots. So I study the detailed physics of the binary interactions and how they, what their outcome is, to try to understand how all these different areas of research are connected and to comprehensively understand how massive binaries evolve. So this is just some example of the kind of topics I'm interested in. In particular, I'm very interested in common envelope phases, and wind acceleration and how that powers X-rays from high mass X-ray binaries. But today I'm going to mostly focus on my research on supernova and how supernova can be impacted by binary interactions, but also how the supernova can impact the binary evolution going on. So just in case you're not familiar with the different kinds of supernova, here is a diagram of how supernova explosions are classified observationally. So basically, if you see a supernova, people take spectra, and based on its peak magnitude or the light curve morphology or the spectral features, we usually classify them into these different subcategories. There's even more smaller subcategories, but I've just listed the main famous ones. So among all of these different kinds of supernovae, so you can already see there's a huge diversity, but the type 1a supernovae are considered to come from explosions of white dwarfs, as you may know, but all of the other ones are probably related to massive stars and their core collapse. And you can see within the core collapse supernovae, there's again a huge diversity in their observational features. And here I just listed them in order roughly on how much hydrogen you see in the supernova. So the top ones like type 2p and 2l supernovae, they are considered to have lots of hydrogen in the supernova ejecta, while these lower ones have much less hydrogen, or even like sometimes they don't even have helium. So this diversity is considered to come from the way the star lost mass prior to the explosion. So the top ones had little mass loss compared to the bottom ones, where they have a huge amount of mass loss towards the end. And these bottom three supernovae, the type 2b's and 1b's and 1c's, are often grouped together as stripped envelope supernovae because they hardly have any hydrogen in their spectra. And there are various scenarios that try to explain why this star loses mass. There's different ways a star can lose mass. Sometimes you can lose it through stellar winds. You can blow off your own stellar envelope, but there's mounting evidence that, at least for the stripped envelope supernovae, most, if not all of them, lost their envelope through binary interactions. So direct stripping from gravitational interactions with a companion star. So here is some theoretical estimates of how many stripped envelope supernovae come from, well, binaries, and what fraction we expect there to be a companion that's still there. And roughly about 70% of stripped envelope supernovae are expected to have a close-by companion at the point of supernova. And if we could find that, that would provide direct evidence that actually the stripped envelope supernova comes from binaries. And indeed, for some supernovae, we actually find companion stars in the aftermath. So this is all good. We now know that stripped envelope supernovae come from binaries. But this wasn't quite end of the story, because the stars we see in the aftermath don't quite match what we expect. So if we go back to this, all of these stars are expected to be, the companions to the progenitors are expected to be so-called main sequence stars, so just normal, boring, hydrogen-burning stars. But if you look at the observed companions, so we only have 5 of them so far, some of them are consistent with being a main sequence star if you plot them on the HR diagram. One is sort of marginally consistent with being a main sequence star, but 2 of them are clearly off. But from a theoretical perspective, we expect that most, again, if not all, companions should be on the main sequence due to many different reasons. One is just simply because the main sequence phase is the longest phase of stellar evolution, but also if you have binary interactions, you would expect the orbit to be quite tight, and you can't really fit in very evolved large stars in a tight binary because it's simply too big. But the companions we see seem to be fairly big, so there's some discrepancy between what we expect and what we see. But again, this is only a problem under the assumption that these stars are actually just normal stars and they haven't really changed what they look like before and after the supernova. But does the companion look the same after being struck by a supernova? These stars are very close to each other, you have a very energetic explosion going on. Well, if you have a huge amount of energy right next to you and slapping you in the face, you would usually have some noticeable features. Just like, yeah, so if you're slapped in the face, you'll get red. So, part of my research is to look at, to do hydrodynamical simulations of supernova ejecta hitting a companion star in a binary. And here you can see one of the simulations where the supernova is coming from the top of the box, and this is the companion star, it's just a main sequence star. And you can see as the shock interacts with the star, it forms this bow shock, but it's a bit hard to see, but there's a forward shock that's going through the envelope, and it's heating the outer layers. Now, in terms of, for example, changing the structure of the star, well, it doesn't really strip off too much mass. At most, we can only strip off about 1% of the stellar mass, so it doesn't really damage the star that much, but it still injects a small amount of energy, quite small. It's not anywhere near comparable to the binding energy of the star, but this amount of energy, small amount of energy, is injected into a small thin layer at the surface. It doesn't go too deep, so you inject a small amount of energy into a small amount of envelope, and that is enough to change the appearance. So here I'm showing results from a calculation I did where after being struck by the supernova, I follow the long-term evolution of this heated star. So originally the star is here, but as soon as you slap it with the supernova, it shoots up into this very luminous but very cool temperature state. So it becomes somewhat like a red supergiant. In this stage, the star's radius is very, very large. But then after a few years, because it's in this over-luminous, very inflated state, it radiates away this excess energy and it quickly shrinks back to its original size. Now, we did this with various different parameters, for example, changing the orbital separation at the point of the supernova. So that changes the amount of energy you inject, but as you can see, most tracks do the same thing qualitatively. So you go up and right on the HR diagram, and then you shrink back after a few years to decades. We did that for a huge parameter set, so different initial companion masses and different orbital separations and so on, but again, everything does the same thing qualitatively. It just goes up and then shrinks back. If you plot the kind of light curve or the time evolution of the radius and luminosity of these heated stars, what happens is they shoot up in radius, stays at the same radius for a while, and then at some point after a few years to decades, it abruptly shrinks and then slowly tails off towards its original size. In terms of luminosity, it's the same. It shoots up, stays at a fixed luminosity for a while, and then abruptly drops and then tails off for a couple of centuries before it retains its original luminosity. Now, this luminosity the star reaches in this inflated state, this doesn't really depend on the amount of energy you inject. This only depends on the original mass of the star. And then what the injected energy determines is how long it stays in this inflated state. So there's not much of a difference in how much luminosity or how luminous you get. It's just how long you stay in this very inflated state. So this is very useful because that means if we can find a companion star after the supernova in this inflated state, and in fact, as I showed before, these discovered companion stars, there's 2 or 3 of them that look like they're not really a main sequence star. They could be inflated. using that luminosity, we can actually constrain what the mass of the companion is. And then if we can follow the star all the way until it starts shrinking, we can constrain how much energy was injected into the star. So here is just what results from our parameter study. We kind of made this formula to describe what luminosity the star becomes depending on the initial mass. So for example, a 10 solar mass star would become this luminous after being slapped by the supernova, which means if we see the companion star's luminosity is this much, that means the initial companion mass was about 10 solar masses, and so on. We also find a tight correlation between the intersected energy, so the injected energy into the star, and the duration of the expansion. So if we can measure when the star starts to shrink, we can use this to figure out what the intersected energy is. And if we know for example, the total explosion energy from different metrics, then we can translate that into the orbital separation. So using post-supernova observations, so we don't need any observations from the previous stage. Just by looking at a companion star after supernova, we can constrain what the pre-supernova orbital separation is. And this is very important for us because there's no other way to really constrain binary interaction physics observationally. For example, this so-called common envelope phase, the main question is how much does the orbit shrink after being swallowed into this envelope? We don't really have a good model for this, but and there's no direct observations of post-common envelope massive star systems. But if we assume that the pre-supernova orbital separation is kind of a result of this common envelope phase, then this is the only way to constrain what the post-common envelope separation is observationally using supernova observations. So here is my attempt at trying to constrain what the pre-supernova orbital separation is based on the information we have from these observed companions. Of course, we haven't seen these stars shrink back to its original size yet, so that's why we can't quite pinpoint which part of these curves the actual stellar mass and the injected energy is, but even just from one epoch of observation, we can place these strong constraints. But if we combine it with other evidence, like some supernovae have information about the progenitor, so we see the progenitor before the supernova, and using that, the orbital separation has to be wider than the stellar radius. So using that, we can kind of constrain which part of the curve the companion should be. Yep.
So, I think this have something difficulty in the observation, because first of all, this supernova are mostly extragalactics, so they are far away, and they also need quite a lot of time to monitoring on the side.
Yep.
The most important thing is about after supernova explosion, the ejecta already almost chemically enrich the inner region environment, and that created dust, and dust was askew those emissions. So the color will actually look quite different from prediction here.
Yeah, so that's a good point. So these companions, they have to be roughly about within 30 megaparsecs. So there's a very limited horizon where we can actually see them, but we already have 5 examples. We just need to keep on looking at them, except we've put in 4 Hubble proposals, and all of them failed. So yeah, if someone can give us time, we can probably constrain these things. But yeah, in terms of dust, so the supernova, the first difficulty is the supernova is still going to be quite bright for the first 3 to 5 years. So the companion has to be at least in this overluminous state for at least 5 years until the supernova fades below the luminosity. So there's a limited window, and so the orbital separation has to be tight enough so that the inflated state is at least longer than 5 years. in terms of dust, I don't think it really matters too much because the dust, like I'm not really using the color information here. I'm only using the luminosity. So if we have full wavelength coverage all the way to JWST bands, then if we know the bolometric luminosity, we can still use these constraints. That's why I kind of intentionally left out the temperature information, because everything gets complicated due to uncertainties in my stellar modeling and also the dust. So yeah, as long as we can have the bolometric constraints, then I think this still works. Yeah. But the main difficulty is, Hubble. Hubble. We need Hubble for these things, and they don't give us time. So yep. Anyway, so using other pieces of information, which I won't go into too much detail, but sometimes you can use different kinds of information to constrain which parts of these curves the companion is actually in, and some of, if you tie it with the spectral information from the supernova itself, we can make some sort of strong inferences. For example, it looks like the type 2b supernovae tend to have wider pre-supernova separations. Wide separation usually means stable mass transfer and not common envelopes, because common envelopes drive the separation in quite tight. On the other hand, this one, which is type 1b supernova, this looks like it has a really tight separation. Maybe it went through a common envelope. So it's very small number statistics at this point, but we can already start deriving important constraints on binary evolution physics from the supernova observations. Now, the other thing that happens after a supernova is not just the ejector slapping the star, but there's a neutron star that's born after the supernova. And the neutron, or sometimes a black hole, but in most cases you give birth to a neutron star. And these neutron stars are known to have really high velocities. These are called neutron star kicks, and the velocity range is typically within like a few hundred to maybe even 1,000 kilometers per second. Now, the reason why neutron stars have high velocities, well, the main idea is that there's lots of asymmetry in the collapsing core. This asymmetry is critical in driving the explosion itself, because we know that 1D collapse simulations never cause any explosions. And if you have very asymmetric flows and convection going on in the supernova, you can have some non-perfect cancellation of the momentum, which gives a recall to the neutron star. Or you can have some asymmetric neutrino emission, which also can drive the neutron star in one direction. And typically this happens on the dynamical timescale of the core. So you accelerate the neutron star in within a second or maybe 10 seconds. So you basically immediately shoot out the neutron star, and that's why it's called a kick. Now, in context of binaries, this is important because it strongly perturbs the orbit. So even if we have an initially circular orbit, so let's say we have initially 1 day orbital period binary with 0 eccentricity. Now first, the supernova ejector gets lost in almost immediately. This already perturbs the orbit strongly, so you have a wider separation, so long orbital period and high eccentricity. And then at the same time, this neutron star is given a kick, so that again perturbs the orbit in some way. And depending on the direction of this kick, which we don't really know, you can have different post-supernova orbital configurations. Like sometimes you go wider and more eccentric, sometimes you go tighter and less eccentric, but basically, yeah, you end up somewhere on this blue tick-shaped region. And actually, in most cases, you actually exceed eccentricity 1 and you just disrupt the whole system and it doesn't stay a binary anymore. And if you're very lucky, if the kick is directed towards the companion, maybe you can sometimes cause a direct collision between the neutron star and the companion. And traditionally, people thought if you just kick a neutron star into a star, it would just immediately fall to the center and lead to a merger and form these things called Thorne-Zytkow objects. But we found that, well, if you choose an impact parameter that's relatively high, so even if you shoot the neutron star into the envelope, it can sometimes penetrate it and come out on the other side. At the same time, the neutron star takes away some material with it, and also ejects some energy from the companion star. So this again could impact the further evolution of this companion because you have some change to the structure and the mass. Here's just an example of the different simulations we did. So this is the distance between the neutron star and this companion, and this is a relative velocity. If this is just a pure two-body problem, it should go in and out on the exact same trajectory. But because if you enter the star, you have some drag force due to the friction between the gas and the neutron star, you always reduce the relative velocity a bit and come out slightly slower. Now here, I shot it in with different angles and different initial velocities, but sometimes you come in and out both on velocities higher than the escape velocity, so you're just on a hyperbolic trajectory, but sometimes you can go in on an unbound orbit and then you'd get decelerated enough to merge, or sometimes you get just decelerated enough that by the time you come out, even though you were initially unbound, you come out on a bound orbit. So you come out, and then if you're on a bound orbit, that means you're going to come in again at some point, then have a second interaction and a third interaction until you finally merge. So we found that these interesting cases where you can have one penetration, one episode of taking away mass. Sometimes you can have multiple penetration episodes doing this multiple times. The amount of mass you take away in this process is fairly small, so it's like 10 to the minus 1% of the stellar mass, which is actually, it looks small, but that is enough to have enough energy. For example, if you accrete that amount of mass onto a neutron star, there's a huge amount of energy that could be generated that could be used for various things. So we came up with 4 different applications that could be important. Traditionally, people thought you just make a Thorne-Zytkow object, but we found that it could make hypervelocity stars, pulsar planets, or even peculiar supernovae. So hypervelocity stars are these stars that we observe in the galaxy that are really fast. They have velocities reaching something like 600 kilometers per second, which is way above the galactic escape velocity. These are all B-type stars, meaning they're about 2.5 to 5 solar masses. Now, there's 2 different scenarios to make these hypervelocity stars. One is called the Hill's mechanism, where you have a binary approaching the central supermassive black hole and gets tidally disrupted, and then one of the stars gets thrown out. But if this is the case, these hypervelocity stars should trace back to the center of the galaxy. But actually, about half of them come from the galactic disk and not the center, so that means it has to be ejected by something else. So the only other way we can think of is the so-called Blau mechanism, where if you have a binary and then disrupt it, you eject it with the orbital velocity. The problem is, these ejection velocities are quite high. They're like, if you just look at the blue ones where they come from the galactic disk, they reach up to 600 kilometers per second. And actually that's above the theoretical upper limit you can get from the normal Blau mechanism. Because the maximum velocity you can get from the Blau mechanism is basically when you shoot the neutron star towards the companion, and then you have this swing by effect and accelerate the companion above the initial orbital velocity so that you can get super fast velocities. And previously people thought, well, if you shoot it into the star, it's going to merge, so you have to just carefully point the neutron star close to the surface so you could get the maximum swing by effect. And because of this, there is an upper limit to the maximum velocity you can achieve, and however you change the mass or the kick velocity or whatever, you can't exceed something like 550 or 540 kilometers per second. There's no way you can go above this upper limit. But in my case, well, we found that you can actually penetrate the star, and if you kind of shoot the neutron star close to the companion, that's where you get the strongest swim-by effect and get the highest velocities. But if you sort of kind of extrapolate this color into the star, you can see you can possibly reach higher velocities. So that's what we found. So this is just a similar diagram where this is the kick angle, so which direction you kick the neutron star, and the maximum velocity you get from the runaway star. This is the same diagram as before, so if you kick it close to the star, this is the maximum velocity you can get. If you allow for penetrations, you can go a bit deeper and have a stronger swing by, which drives you to higher velocities, and we found that you can go up to like 10% above the classical upper limit that we had. 10% is just enough to explain the highest observed hypervelocity star we have. So this kind of resolves the hypervelocity star problem. So we just did some very rough rate estimate. So I'll just skip the assumptions we made, but based on some reasonable assumptions about the binary orbital separation before the supernova and the kick velocities and directions, and multiplying it by the core collapse supernova rate and the lifetime of stars, we expect something like 1 to 10 hypervelocity stars in the galaxy. The hypervelocity meaning hypervelocity stars above the theoretical upper limit, which is like 600. And the observed number is like 1 or 2, so it looks like maybe this is consistent with what our scenario where we think these stars come from penetrating penetrating Blau mechanism systems. Now the other thing was, we thought, well, maybe we can make pulsar planets. So if you, I don't know if there's any exoplanet people here, but the first observed exoplanet is actually a pulsar planet, so a planetary system around a neutron star. And now there's something like maybe about 10 or more pulsar planets that have been observed. And there's several different scenarios that have been proposed to explain how you can make a planetary system around a pulsar, because a pulsar always experiences a supernova. So you have to make this planetary system after the supernova, because otherwise you'd probably just blow it away. Among these, we came up with a new scenario where, well, if you penetrate the envelope of the companion, we saw it takes away some mass, and this mass has some angular momentum, so maybe you can make a protoplanetary disk from this captured material, and this can make the planetary system if this binary is on an unbound orbit, so it never comes back again. So just to check, from our simulations, we looked at how much mass we captured and how much angular momentum was in the captured material. At least within the models we computed, there was enough mass and angular momentum to form the 3 planets in this famous, I think it was this famous system called PSRB 1957. So again, maybe the first observed exoplanet could have come from this envelope penetrating binary. Again, we did some very rough rate estimates. So here we just needed some assumptions on the initial binary orbital separation and the kick strength and the directions, but we expect something like 10 to the minus 5 to 10 to the minus 3 of neutron stars should host these planetary systems. The observed, we don't have an upper limit because we have one planetary system out of a few thousand pulsars. I said there's about 10 observed, but most of these are like Jupiter masses, so probably comes from a different channel. We can't make Jupiters in this scenario. But yeah, this upper limit is within, well, above our estimated rate of these planetary formation. So maybe pulsar planets come from this envelope penetration case. Another thing is, well, maybe if you have the accretion onto the onto a neutron star, you can have accretion feedback powering the supernova from inside. So you can create multiple bumps in the supernova because, as I said, in some cases you have a bound binary having multiple penetrations, multiple accretion episodes causing multiple bumps. And actually there's a few supernovae where we see this, so this again could be proof that supernovae are occurring in binary systems. Furthermore, if we combine this with my previous work where you have an inflated star, inflated because of the supernova energy injection, even if you don't directly penetrate the envelope of the companion star, you can interact with the inflated part of the envelope, which has an extremely low density, and this is enough to have some accretion feedback or accretion onto the neutron star and cause some multiple bumps in the supernova. So basically what happens is you slap the companion with the supernova, the companion gets swollen up, but the swollen up part of the envelope is very low in density, so it doesn't really impact the orbital separation. It keeps on sweeping up material in this envelope, and you can do this multiple times. So I think there was a recent supernova called 22 JLI, which was the first supernova showing these 15 bumps in the supernova light curve. Nobody really knows what happened, but this could be the first case where we see interaction between a swollen up envelope with a newborn neutron star in a binary. So at the moment we're just working on some 3D simulations trying to verify the scenario, but this is still work in progress. I don't know how much time I have left. Is it 10 more minutes? Or is it 10? Okay. Right. So far I've talked about envelope or supernova ejecta-companion interaction and the effect of neutron star kicks on binary systems. Now this is basically what constitutes what what binary evolution people use to try to explain all the observed systems and observed massive binaries. But nowadays we're finding systems that we just simply cannot explain with this neutron star kick and normal binary evolution like pipeline. And this is called Gaia neutron star 1. So there's a neutron star system that was found with Gaia. And the problem is this has a very wide orbit with a very low eccentricity. Eccentricity is below like 0.1 or something. Now usually if you have a low eccentricity and wide orbit, that usually means there was a very weak kick. So if the kick was strong, you would get a really high eccentricity, wide orbit. Well, to have a wide orbit, you get that very high eccentricity. But low eccentricity usually means you have a very weak kick that only perturbs the orbit very slightly. But if you look at this system in the galactic frame, well, it's on a very eccentric orbit. So even though the binary orbit itself looks like it was weakly perturbed, the whole system was strongly perturbed to be on this very eccentric orbit around the galaxy, which implies a very strong kick. So which kind of implies there's a contradiction between what we know between these, well, what we infer from these two different constraints. And actually, I think nobody, has any idea how to explain this. And I was also thinking how to make this, but one morning I woke up and I was just swiping my phone, looking at Google News, and there was a paper that was from the 70s, but I don't know why it showed up on my Google News feed. And this actually, was very mind-blowing for me, because actually in the 70s there were scenarios that tried to explain the neutron star kicks in a totally different way. So previously I said neutron star kicks come from the asymmetry in the collapsing core. So this occurs on the dynamical timescale of the iron core of massive stars. In the 70s, people had a different idea that, well, this was actually, the neutron star was accelerated on the spin-down timescale, and if the spin-down luminosity from the neutron star, so if you have a dipole magnetic field and you spin it, you have some luminosity going out, which is what causes the spin down as a neutron star. But if this is asymmetric, you would have a slow, you have asymmetry in the pointing flux, which causes a slow acceleration of the neutron star. Now this is somewhat supported by recent observations, because with the nice X-ray telescope, we see that the surface hotspots on a neutron star is very asymmetric. It's not, if it's a perfect dipole, we would expect the hotspots to be perfectly opposite to each other, antipodal, but it's actually offset. So we kind of know already that magnetic fields are not symmetric, or they're not dipolar, which means if you spin that, you would accelerate the neutron star to some degree. There's another scenario called the neutrino rocket, which says the neutrino emission from the cooling phase is aligned with superfluid vortices, and the superfluid vortices are aligned with the rotation, so you'd accelerate the neutron star in one way. But either way, these scenarios accelerate the neutron star on months to year timescales, and not the 1 second that we traditionally usually understand. And this is very important for binary evolution, because we can't treat it as an instantaneous kick anymore. It's a very slow acceleration of the neutron star. So if you look at the orbital periods of binaries containing neutron stars, well, the most tightest binaries are a few hours. So this is still much longer than this few second timescale of the normal kicks. So that's fine in terms of, the usual kick mechanisms are instantaneous. But most of these binaries have orbits less than 1 year, which means if we take these rocket-like models, or these slow acceleration models, we can't make this instantaneous approximation anymore. It has a very different impact on the binary orbit. So yeah, my question was, well, what happens if the kick, if we can't assume it's instantaneous anymore, how is the orbit perturbed? Now it turns out that this is a long-standing problem since the 1700s. I think it was originally found by Laplace or someone, who found that this is one of the 3 only integrable two-body problems. So this is called the classical Stark problem. But I'll skip the details, but I actually found the analytic solution to this classic Stark problem, and it turns out that you can describe the evolution of a binary with one star being accelerated in one direction very slowly. You can just describe it in a very simple way. Now basically what happens is you have a binary orbit, and if you accelerate one of the neutron star very slowly, slower than the orbital period, then the orbital plane kind of rocks around the direction of the acceleration. At the same time, the eccentricity of the binary goes up and down. During this evolution, there's no change in the orbital separation or the orbital period. So the way it impacts the orbital orbit is very different from the instantaneous kicks that I introduced before. Now the amount of eccentricity, the amplitude of this eccentricity oscillation is strongly dependent on the direction of the acceleration and the initial eccentricity of the binary. For example, if it's a circular binary and the acceleration is aligned with the angular momentum, there's no change to the orbit, there's no eccentricity change. In a supernova, you're always guaranteed to have some sort of initial eccentricity, because you always have some mass loss, which guarantees you to have some eccentricity. You still have a natal kick, so the rapid kick. These two scenarios are not mutually exclusive. You can still have the normal core collapse kick, and then you can have a slow acceleration rocket-like kick in the same system. So if we combine these three, we can reach very different parameter regions that we could never reach in our previous normal kick paradigm. So I'm coming back to this diagram again. So after a supernova, we always have mass loss and a kick, which with just normal instantaneous kicks, you can only cover this blue ticked region, which is very narrow in terms of this parameter space. We can never go into this region, below this black curve. This is simply impossible mathematically, because you cannot ever widen the periastron distance with an instantaneous kick. But if we replace this kick with a rocket, so if we just have mass loss and then a slow acceleration, you can actually cover a different parameter region, which is actually quite boring. You keep the orbital period and you just go up and down in eccentricity. But you can still go below that black curve I showed before. The most interesting thing happens if you combine the kicks and the rockets. So after the kick, you go somewhere on this the blue dotted region, and then you accelerate it with a rocket. You can cover much wider range in eccentricity and period on this period eccentricity diagram, which was impossible with previous kick models. So, what was I going to say? So if we just overplot the observed Gaia neutron star systems, which is around here, you can never explain it with the kick models. So this was a puzzle for all of us binary evolution people. But with this new rocket-like acceleration on top of a kick, we can easily explain the existence of these Gaia neutron stars. And we also don't need to drastically change our understanding of everything else, because the amount of rocket acceleration doesn't need to be strong. We only need like 10% of the kick velocity to be added onto the system in order to reach these low eccentricities. So everything else, like in this region, we don't really need the rockets. We can still just explain everything with kicks, like X-ray binaries and all the tight orbital systems we see. But these wide systems come from a combination of kicks and rockets. So I think this kind of opens up a whole new area, because there's all sorts of systems that we're now discovering with Gaia that simply we cannot explain with just traditional binary evolution theory, but now we have a new way of trying to modify orbits in different ways. It's also interesting that you can go up in eccentricity above the blue tick. And this means if you can go to eccentricity 1, you can drive mergers as well, because eccentricity 1 just means like head-on collision. So you can induce mergers from this scenario as well. So I think I've used up my time, so I'll just put in my summary. So basically, supernova explosions, almost all of them come from some sort of binary system. So binarity in a supernova are kind of unsplittable. I showed that supernova ejecta can impact the evolution of the companion in various ways. Also, the neutron star kick and rockets could impact the binary orbits in very non-traditional ways that we probably need to take into account in future research. So yeah, thank you for your attention.
Thank you very much. Is there any question for Ryo? Any comments? So Ryo, I have a
I have two questions. First is about the Gaia neutron stars topic. So do you have any physical constraints on the supernova progenitor or companion star?
So observationally, so all of these stars are one solar mass main sequence stars. This is simply because Gaia is good at observing sun-like stars. We don't know anything about the pulsar. This was only astrometrically confirmed neutron star, so we just see the motion of the sun-like star, and you can place a constraint on the mass of the unseen companion, and if that mass is above the Chandra-Zykow mass, they classify it as a neutron star. So we have no idea of the exact mass of the companion. We actually don't have a confirmation that it is a neutron star. It's just an invisible 1.5 solar mass something. So we don't have any observational constraints. But, yeah.
Also you cannot reject any supernova types on something like type 2 or type 2B or
No.
No. And the other question is about the other different topics. So in the first section you described about the interaction between supernova ejecta companion star and you said that after the supernova, after the heat of the supernova ejecta companion star, then the companion star inflates. So I'm wondering what's the physical process of the inflation of the components. So is it because the energy deposition from the supernova shock to the component star, or is it because the stripping of the interplay of the component star, or both combination of both of them, or anything else?
This is purely due to energy injection. So you have some excess entropy in the outer layers, and the high entropy drives the star out of thermal equilibrium, so it just needs to expand adiabatically.
Any further questions? Comments? So really, I have a few comments, and actually I think it's difficult to form planetary in the neutron star in the scenario you mentioned, because we have like a Shiwei doing the planetary formation, and usually associated with the star formation. You can just grab a mass around the neutron star and you form planetary. I don't think it's potential. I mean, it may be possible, but I think it's very difficult in terms of, because you form molecular cloud, and you form the star, you form the protoplanetary disk, stellar disk. So that's the things. Another thing is in here you mentioned several of the cases using the neutron star, for example, to accelerate the hypervelocity stars. But do you consider the tidal effect?
So for the first question, so admittedly I'm not a planet person, so I am agnostic about how the planet is formed, but we do see gas disks around neutron stars. Like, I think there's one or two neutron stars we actually do see a gas disk. So there's some way.
Is it observationally?
Yes, yeah, observationally.
Is it a accretion disk?
No, not an accretion. It's like a extended. Not. I don't think they call it planetary disk, but it's a gaseous disk.
Anyhow, actually the first thing, the prime first discovered is actually orbiting around neutron star. So we need to construct some models.
Yes.
So for
Yeah.
But I saw my point is think about this the planet already have been there, maybe already surrounded by the pre-explosion the
So
stars.
at least for this system.
They'll form later in the.
No, so for this system, so all the planets are within a Mercury orbit. Mercury orbit, likely means, well, it definitely means it has to be inside the envelope if it ever became, like a red giant or anything. So I don't think we can explain it with, primordial planets. It has to be after the supernova. Yeah. And, sorry, the second question was, sorry, can you repeat the second question again? So not the planets, but...
The second question is any tidal interaction?
Ah, yeah. Well, I mean...
When you stripping because actually we did some simulations to shoot the neutron star on the main sequence star. Actually, what we see is when the neutron star close into the star, the main sequence star, there's already some of the mass transfer occurs.
Yep.
It's not just like a cutting or through, like a slice through the star. So
yeah, we also do see the
yes.
there's some mass transfer.
Mass transfer stream already. And because this is can it just affect the result for the hypervelocity? But because you want to have a slingshot.
Yeah, but I mean, there's no need to put in explicit ties into a 3D simulation. Like, it's kind of automatically in there. So I don't quite understand. We do see penetration, and there's enough acceleration to explain at least 640. So yeah.
Yeah. Any other questions or comments? Okay, so if not, let's say it's real again.